Hi everyone. Today we're going to be starting Chapter 7. The first sections we're going to be talking about is 7.2, and we're going to be working with indefinite integrals and initial value problems. So before we talk about exactly what indefinite integrals are, I want you to think of this question. So what if I asked you to name all of the functions whose derivative is 2x. Okay, so if we were asked to name all the functions whose derivative is 2x, the first thing we might think to do is anti-differentiate 2x, because we know if we're looking for the function whose derivative is 2x, we should anti-differentiate this function. So if I do that, we're going to follow our normal power rules. I'm going to add 1 to the exponent, which is going to make that 2. And then I'm going to divide 2 by my new exponent of 2, and I get x squared. So x squared is certainly one function whose derivative is 2x. But now I want us to think, what about the function f of x equals x squared plus 5? If I were to differentiate that function, my first term is 2x, and because I have a constant here, that would go to 0. So its derivative is also 2x. And so from there, we could go on and on. I could come up with a function x squared minus 3. Its derivative is also going to be 2x. So we could do this exercise over and over, and what we would notice is all of the functions whose derivative is 2x just differ by a constant value. So all the functions whose derivative is 2x are going to differ by some constant value. And if you keep this little example in mind, it's going to make what we're talking about a lot simpler to understand. So let's go to the notes here. So we're talking about indefinite integrals. So sometimes we're asked to integrate a function where the bounds are not provided. So in other words, when we see our integral, we're used to having upper bound and a lower bound, a number here. But sometimes we're not given those bounds. So in this case, we call this problem an indefinite integral. So an indefinite integral is just an integral where we don't have numeric values for those bounds. So when we perform this integration, we still find the antiderivative, but we need to add a plus c to the end of the antiderivative to represent a constant that is unknown. And so that's exactly what we were talking about here. When we took the antiderivative, we got x squared, but we add this plus c to then account for all these constants that could be in that place. So as long as you know your antiderivatives, today's lesson is really going to be pretty simple. We're just going to be adding on a plus c every time we antidifferentiate, because you'll notice I don't have any limits here. So really quickly, I want to make a note here. What we're talking about today is indefinite integrals. Okay? And so they're going to look like this: integral of f of x dx, right, with no bounds. And so I want us to understand is the answer to this is a family of functions. That plus c means we have a whole family of functions for our antiderivative. Now, on the other hand, we have our definite integrals, which is what we were working with in the last chapter. And so here we do have an upper and a lower bound, or limit of integration. When we do a definite integral, now our answer is just a number. So I want to be really clear on the difference between those two types of integrals. But like I said, for today we're working with indefinite, so we're going to take the antiderivative and just put on a plus c at the end. Anytime we have an indefinite integral, we need to have that plus c. So for my first example here, the integral of x squared minus sine of x dx, we're just going to antidifferentiate like normal. So I get x cubed over 3 for my first term. Now, the second term, since this is a negative sine x, I know cosine has a derivative of negative sine, so my second term is going to be a positive cosine x, and then we're going to add in our plus c. And that's all there is to it for these indefinite integrals. For number 2, I have 5x dx. Remember, that's the same as 5 times the integral of x dx. So I'm just going to have 5 times the integral of x dx is just x squared over 2. And I could just write that as 5x squared over 2 plus c. For number 3, again, this is the same as 4 times the integral of cosecant of x, cotangent of x dx. So I have 4. Now again, the function whose derivative is cosecant x, cotangent x. Well, I know the derivative of cosecant x is negative cosecant x, cotangent x. Since I don't have a negative here, it's going to be in my antiderivative. So I have negative 4 times the cosecant of x plus c. Okay, for number 5, again, I'm going to be careful of signs here. I know this is going to be negative cotangent of x plus c. And remember, guys, if these antiderivatives aren't pretty automatic by now, you really need to go and make some flashcards or do some practice. These should be automatic at this point in time. For number 5, I'm going to rewrite this so it's a little more familiar. I have negative 4. X to the negative 1 is just 1 over x dx. And so now hopefully we know the antiderivative of 1 over x. We're just going to have negative 4 times the natural log of the absolute value of x plus c. For number 6, here I can use my power rule. I'm going to rewrite this as x to the negative 2 dx. So now if I add 1, I'm going to get x to the negative 1. And then I divide by that, so I get negative x to the negative 1 plus c. Or I can just say negative 1 over x plus c. Either form is fine. Okay, number 7, hopefully we recognize pretty easily. This is just inverse tangent, because this is the same as 4 times the integral of 1 over 1 plus x squared dx. And that's just 4 times the inverse tangent of x plus c. Here we have 3 times the integral of 1 over the square root of 1 minus x squared dx, which is our inverse sine. So 3 times the inverse sine of x plus c. Here, this is the same as 3 times the integral of 2 to the x dx. So now I have 3 times, well, I know this derivative is 2 to the x over, the antiderivative, 2 to the x over natural log of 2 plus c. And for the last one, e to the x, this is always a nice and easy one. Our antiderivative is negative 3 e to the x plus c. So again, the big idea here, the only thing that's new is if we have an indefinite integral, which means no lower limit or upper limit of integration, we always have to have the plus c. So let's take a look now at some initial value problems. Sorry guys, lost my book here. All right. Here we go. Okay, now for initial value problems, when a specified initial value is provided, we can solve to find the value of the constant c in our integral problem. So all this means is that we're going to be given some information so that we can solve for c. So our first step is going to be just the same as what we were doing. We're first going to anti-differentiate, and because this is indefinite, we're going to add a plus c to our answer. So 1 over x I know is the natural log of the absolute value of x, minus 1 over x squared. I know that's going to give me plus 1 over x for my antiderivative. And then for 6, it's going to be 6x, and I put my c on the end. So there's my indefinite integral. Now, this problem is telling me that y is equal to 0 when x equals 1. That's my initial condition. And I'm going to use that to solve for c. So I'm going to take my antiderivative, and I'm going to set that equal to y. So y is equal to the natural log of the absolute value of x plus 1 over x plus 6x plus c. And now I'm going to substitute those values for my initial condition. So y is equal to 0 when x equals to 1. So everywhere I have an x, I'm going to plug in 1. So natural log of 1 plus 1 over 1 plus 6 times 1 plus c. So I get 0 is equal to, well, no, natural log of 1 is just 0 plus 1 plus 6 plus c. So I get 0 is equal to 7 plus c, which means that c is equal to negative 7. So now for my final answer, I can plug c into my solution, and I have natural log of the absolute value of x plus 1 over x plus 6x plus c. And that's my answer to the initial value problem. Oops, sorry guys, not plus c. The plus c we said was minus 7. Sorry about that. Okay, let's just do a couple more of these. For number 2, so my antiderivative, the antiderivative of secant t tangent t is just 4 secant t. Antiderivative of e to the t is e to the t. And 6t is going to be plus 3t squared. And we put on our plus c. So now I'm going to write this as y equals, so 4 secant of t plus e to the t plus 3t squared plus c. And I'm going to substitute my values from my initial condition. So y is equal to 5 when t is 0. So 4 times the secant of 0 plus e to the 0 plus 3 times 0 squared plus c. We can go ahead and simplify and solve for c. So secant of 0, I know secant is 1 over cosine. Cosine of 0 is 1, so secant of 0 is 1. E to the 0 is 1. 3 times 0 squared is plus 0. And I have plus c. So what I get is 5 is equal to 5 plus c. So in this case, for this problem, c is equal to 0. So my solution to the initial value problem is just 4 secant of t plus e to the t plus 3t squared. And we're done. All right, one more, and then we're done for today. Again, a lot of this is just going to be dependent on how good you are with these antiderivatives. These should be pretty quick problems. You shouldn't have to spend a lot of time coming up with these antiderivatives. So secant squared of x, I know I have 5 times the tangent of x. Now, let's see. For my second term, I know square root of x is the same as x to the 1/2. So if I add, I don't know why my x is up here, tangent of x. If I add 1 to 1/2, my new exponent is going to be 3/2. If I divide 3/2 by 3/2, I just have a minus 1. So 5 tangent of x minus x to the 3/2 plus c. So here I have my function, 5 times tangent of x minus x to the 3/2 plus c. I'm going to substitute the values from my initial condition. So y7 equals 5 times tangent of 0 minus 0 to the 3/2 plus c. Tangent is sine over cosine. We know sine of 0 is 0. So this tangent of 0 is just going to be 0 minus 0 plus c. So we get c is equal to 7. So my solution is going to be y equals 5 times the tangent of x minus x to the 3/2 plus Keep doing that. Sorry, guys. Not plus c, plus 7. So tomorrow we'll do some speed dating to practice with this because really, like I said, these antiderivatives should be pretty automatic. If you're realizing that they're not, I would spend some time tonight reviewing those so you're ready for the activity tomorrow.